right, so welcome to your review warm-up that's going to kind of tie together everything from this Unit 2 that we've just been doing. So let's start with the most recent stuff. 20 students were asked to guess the age of a man in a photograph. Here are their guesses. Are these guesses approximately normally distributed? Please provide evidence to support your answer. All right, so first things first, let's get to the important stuff. I don't actually know how old this guy is, so I'm sorry if you're currently sitting there being like, yeah, but what's his real age? I don't actually know. So I just Googled like random guy, and this is the picture that I chose. So I apologize for not being able to give you a definitive answer. But when we're determining if something is normally distributed, we sort of have our three-step process. So step one is the histogram step. So let's take a look. I've got the data entered into L1. I'm going to go to stat plot. I'm going to switch it over to the histogram, and then I'm going to go to zoom 9. All right. And if I sketch that really quick, all right. Again, I don't need like an exact sketch when you're doing this. It's really just to get a general idea of the shape. All right. And if we're kind of commenting on this, we can say, all right, well, you know, it looks symmetric. It's unimodal, which is good. And it doesn't appear that there are any outliers, at least going by the picture. Now, we also kind of want to compare the mean and the median just to make sure that they're in the same ballpark. So I can go to stat calc, one variable stats, and I can see the mean is 42.7. So I'm going to say x bar is 42.75. And the median is 43. So those are also relatively close, which is a good sign. Okay. The next thing that we can take a look at is the 68, 95, 99.7 check, all right, which is where we see how many observations fall within 1, 2, and 3 standard deviations of the mean. So we already have our mean is 42.75. So x bar is 42.75. And then our standard deviation, I'm going to use the sample standard deviation because we just randomly picked 20 people here, is 4.15. We'll round it to. So what we're going to do is we're going to find our cutoffs. We're going to say 42.75 plus or minus 4.15. Then we're going to say 42.75 plus or minus 2 times 4.15. And then we're going to say 42.75 plus or minus 3 times 4.15. And then we just have to get what our various cutoffs are with those calculations. Okay, so this first one would give us a range of 38.6 to 46.9. The second one is going to give us a range from 34.45 to 51.05. And the third one is going to give us a range from 30.3 to 55.2. All right. So then we're just going through and we're counting how many of these observations fall in each of these ranges. So for this first one, I mean, we're basically looking for 39 because 38 would technically be too low. And we're looking at 46 because technically 47 would be too low. So we're looking from 39 to 46. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 38 would be too low, but 13, 14. Okay, so the first one was 14 out of 20, which is 70%. So that one's pretty close, right? Then once we add this extra range, so now we can include ones that go down to 35, because again, 34 would be too low, and we can include ones that go up to 51. So that's going to give us an extra 1, 2, 3, 4, 5. All right, so that's now going to be 19 out of 20, which is 95%. And then when we add the last one in here, that's finally going to let us get this one right here, which is going to give us 20 out of 20, which is 100%. So we can see that, again, this follows pretty closely with what we'd expect with the 68, 95, 99.7. So at this point, we should probably expect our normal probability plot to look pretty good. Put that up here. Normal probability plot. All right, and again, to get that, I can go to second y equals. I can go back to my stat plot, and it's the very last choice. And then I can go to zoom 9. And we're going to see that if I sketch this out here, all right, I've got that one, and then I've got a whole bunch of ones like this. All right. And this right here is very linear. So all three of these things, all three support the data being normal. So again, none of this is very difficult. I mean, step 1 and step 3 is just bringing up a graph in your calculator and looking at it and analyzing it. And then step 2 is just some addition, some subtraction, and then counting, right? So again, none of it's difficult to do, but this is sort of the process we can go through to ensure that our data is normally distributed. All right, now working backwards, number 2 looks at some of the normal CDF or NCDF and inverse norm type questions. So it says a study of elite distance runners found a mean body weight of 63.1 kilograms with a standard deviation of 4.8 kilograms. Assume the distribution is approximately normal, because again, none of this works unless your data is normal. What percentage of the runners have body weights between 48.7 and 67.9 kilograms? All right, so step 1 is to turn both of those into z-scores. So we know that z equals the observation minus the mean divided by the standard deviation. So our observations were 48.7. All right, so subtract that by 63.1 and divide by 4.8. And then our other observation was 67.9, and we're going to subtract that by 63.1 and divide by 4.8. Okay. So let's see here, 48.7 minus 63.1 divided by 4.8 is -3. And 67.9 minus 63.1 is going to be 4.8. So that just is going to tell us that it's 1 standard deviation above the mean. All right. So what this is saying is what percent of the observations are from 3 standard deviations below the mean, which is basically way down here, to 1 standard deviation above the mean, which is way up here. So we should be expecting an answer up above 50% because we're shading more than half the curve at this point. But we can make sure, so NCDF from -3 to 1 when the mean is 0 and the standard deviation is 1. We go to our second vars, all right, which is the distribution menu, NCDF from -3 to 1 when the mean is 0 and the standard deviation is 1. And that will give us 0.8399, but when we round that up, we're actually going to end up with 0.8400, which you can also think of as 84%. All right. So that's one example. This one says, what percentage of runners have body weights below 60 kilograms? All right, so we're still going to start by turning this to a z-score. So we have z equals observation minus mean divided by standard deviation. All right, so we've got 60 minus 63.1 divided by 4.8. 60 minus 63.1 divided by 4.8, negative 6458, right? Negative 0.6458. If you also just use negative like 0.65 here, it's fine by me. I wouldn't really round it any more than that, but if you wanted to just go to the 100th, I would be fine there. So again, just visually so that we have an idea of what's going on here. If this is 0, negative 0.6 is probably going to be somewhere about there. So we're looking at this part of the curve. It's not half because we're not going all the way up to the 0, but it also shouldn't be too tiny. So again, we'll check it. We'll see what it is, but this at least gives us a frame of reference. Now, when we're doing one of these where it says below a value, when we go to normal CDF, we're going to be putting our lower value in as like negative 999. And again, that's effectively negative infinity because that many standard deviations below the mean is, you're talking about such tiny amounts of area that it won't show up in the calculator. And then we're going up to negative 0.6458, mean of 0, standard deviation of 1. And that gives us, well, so here, let me write out the work for it first. So negative 999, negative 0.6458, mean of 0, standard deviation of 1. And that gives us 0.2592. 0.2592 or 25.92%. All right. This next one is basically the same question. It's just going in the other direction. So this time it's saying above. So we'll still do z equals the observation minus the mean divided by the standard deviation. This time our observation is 70. Our mean is still 63.1. Our standard deviation is still 4.8. So let's see here, 70 minus 63.1 divided by 4.8, 1.4375. 1.4375. Again, if you round that to 1.44, that's fine. But with only 4 decimals, I'm just going to keep them all. Again, if we visually think about this, all right, this is like probably 1 standard deviation where that curve sort of goes from bending down to bending back up. So 1.4 is probably this part right here. So we're not expecting this to be a really large answer because most of the area is going unshaded. And if we check that out, this time 1.4375 is going to be the low end. And we're going to go to positive 9999 when the mean is 0, when the standard deviation is 1. So again, this time the 1.4375 is my lower, the upper is the 999. The mean and the standard deviation stay the same. And we get 0.0753. 0.0753, or written another way, 7.53%. Last but not least, calculate and interpret the 45th percentile of the runner's body weight distribution. So this is a different question. Right? This is saying you have 45% of the curve shaded in. All right, that corresponds to 45% of the curve. What is the z-score that goes with that value? And then once we get the z-score, we're going to turn it into an actual body weight. All right, so this requires inverse norm. We know that the area is 0.45 or 45%, because the percentile is the percent below. The mean is still 0. The standard deviation is still 1. So we go to the same exact menu, only we choose choice 3. Our area is 0.45. Our mean is 0. Our standard deviation is 1. So this gives us negative 0.1257. And just a reminder that this value right here is a z-score, right? It is not a percentage. It is a z-score. So we're now going to use that z-score and change it into an actual body weight by saying, all right, negative 0.1257 equals x minus the mean, which is 63.1, divided by the standard deviation, which is 4.8. All right, so I've got this whole thing in my calculator, so I'm actually just going to keep going and just say times 4.8, and then add 63.1. And then I'm just going to write out this full answer here straight from my calculator. Again, rounding, I'm not going to get too hung up on as long as you do it correctly. So x equals 62 point, I'll just keep the 4 decimals, 0.49, whoops, 0.4968, and that's in kilograms. All right, so just a reminder, NCDF gives you percentages, inverse norm gives you a z-score, and then we change that back to whatever unit the problem is actually dealing with. So in this case, 62.4968, or basically 62.5 kilograms, would be the 45th percentile. Okay, so this is the type of question that you might see on your exam. Like, you do have to know how to do this in some sort of context. How to use NCDF and inverse norm in some sort of context. All right, let's take a look at the back, some of the earlier stuff. Below is a cumulative relative frequency graph for the length of time a group of 62 students spent on the Algebra 2 trig regents. What is the median time spent on the exam? What is the IQR time spent on the exam? So again, this was basically the same question that was on your quiz, just a different graph. So remember, the median is really the 50th percentile, and IQR is really the 75th percentile minus the 25th percentile. All right, and this graph can give us percentiles. So if we wanted the median, we would go to 50%. This would be our 50% mark. We would go over until we hit the graph. Then we would go down. And we would say, all right, they spent, let's say, if that's 75, there's 25 minutes, that's probably 87 and a half. They spent about 90 minutes or so on the exam. Now for the IQR, we've got to find a few different things because IQR is Q3 minus Q1. Q3 is going to be up here at 75%. So if we go over and then down, we could say that maybe Q3 is about like 110. Again, we're just kind of roughly estimating here. It's more the fact that you know how to use one of these is what I'm concerned with. And let's say that 25% is right about here. All right, that corresponds to, yeah, we'll just say 80 to just keep it easy for right now. So our IQR would be about 30 minutes. And again, you might have slightly different answers here. The main thing is that I'm looking to see, is your line at about 25%? Is it about 50%? Is it about 75%? And then you can already tell that these aren't totally straight. So obviously I'm not getting exact answers, but it gives me a ballpark. It gives me a general idea of where things fall in this distribution. Okay, so you will still need to know how to read one of these graphs. All right, let's take a look at the next one that deals with transformations. According to these data, the mean time students spent on the exam was 94.1 minutes, and the standard deviation was 24.23 minutes. Suppose the exam proctor realized after compiling these data that he had used the wrong start time in his calculation, so that each value for the time spent on the exam needs to be reduced by 15 minutes. He also wants to express the time in hours rather than minutes. Find the mean and standard deviation of the transformed data. So there's two different transformations here. They want to reduce the time by 15 minutes. So they want to subtract 15 from everything. And then they want to convert it to hours. So to convert to hours, you're going to take this value and divide by 60 for everything. Now, what we learned is that when you add and subtract a constant, it only impacts the mean. The standard deviation is unaffected by adding and subtracting constants. And when you divide or multiply, it impacts both the mean and the standard deviation. Okay, so as far as what this is actually going to do, our mean started at 94.1. We're going to have to do both. We're going to have to subtract 15. And then after we've subtracted 15, we're going to divide by 60. We have to do both of those. All right, so 94.1 minus 15 divided by 60. Let's say 1.32. So 1.32 hours would be our new mean. Now the standard deviation, we do not subtract the 15, right? That does not impact standard deviation. So the only thing we do is divide by 60. So we're going to take the 24.23, we're going to divide by 60, 24.23, we're going to divide by 60, and we're going to get 0.40. I only use two decimals here, so I'll only use two decimals here. So we'll call this 0.40 hours. All right, so it's important that you know how to do these transformations. And the main thing that you have to remember is that adding and subtracting only impacts the mean. Multiplying and dividing impacts both of them. Okay, so these would be your two answers. All right. Number 4. A normal probability plot for the amount of lactic acid in a sample of 30 pieces of cheese is shown below. Is the lactic acid distribution approximately normal? Justify your answer. So again, you're drawing sort of a line through the bulk of the points. And it's another one where you don't want to get too crazy. Like, don't try to overanalyze it. These are relatively linear. Is it perfectly linear? No, it's not perfectly linear, but it's pretty close. So yes, the distribution is normal because the plot is relatively linear. All right. If I'm giving you a question of, if I'm giving you one of these normal probability questions and the answer is that it's skewed, I'm not going to make it ambiguous. All right. So if I'm showing you something is right skewed, all right, you're going to have something like this, where it's pretty obviously right skewed. All right. Nobody's mistaking this one right here as linear. There's a pretty obvious curve. All right. This would be right skewed. And the reason it's right skewed is because the points are ending off to the right. Right. If I give you something that's left skewed, again, I'm not going to make it ambiguous. It's going to be very obvious that it's left skewed because those points are falling to the left of the main line. All right, so again, if it's curving off and the points are ending up to the right of that like center line, then you know it's right skewed. If the points are ending up to the left of that main line, then you know that it's right skewed. But it won't be like this where it's like, yeah, is it not? Like, if you get something like this, you kind of just have to, see the forest through the trees and say, all right, this is relatively linear. All right, I'm going to make it obvious whether it's right or left skewed with a more dramatic curve. This is not a big enough curve that I would say that I would worry about calling this skewed in any direction, one way or another. All right. So again, this is the sort of stuff that you need to know for your test. You need to be able to read one of these. You need to be able to do transformations. You need to be able to read one of these graphs. You need to be able to figure out whether something is normal. And you definitely need to be able to do inverse norm and normal CDF, right? Number 2 is probably where most of the points on the test are tied up. So if you don't know how to do z-scores, inverse norm, normal CDF, you really need to go back and watch some of those old videos because it's going to show up again, and again on the test. All right. So good luck and let me know if you have any questions. All right. Bye.